Hello maths fans, I'm Dr. Tom Crawford, a mathematician at the University of Oxford and the University of Cambridge, and today I'm taking on the challenge of a maths exam from the year 1866. That's right, this exam is over 150 years old. This is the New York State Arithmetic exam, dated November the 8th, 1866. There are a total of 24 questions, but otherwise there are no instructions. So I have no clue, for example, how long I have to complete those 24 questions. I'm going to assume I'm not allowed to use a calculator, probably because they did not exist in 1866, or at least the electronic version that I would want to use definitely did not exist. Most of these questions are likely to be a little bit ridiculous, probably involving weird units that I have no idea about, but we'll see. As usual, I am going into this completely blind because that's part of the fun. Right, let's do this. I'm actually a little bit scared about what this is going to entail. Question 1. Write in figures each of the following numbers. Add them and express in words or numerate their sum. Okay, so what have we got? We have 56,000 and 14 thousandths. Okay, now already I have no idea what a thousandth means in the language of 1866. In modern mathematical language, it would mean 1 divided by 1,000, 14 of those. So it's like part of a whole number. I'm going to use that definition. I have no clue if that's what I'm meant to do, but I can only interpret it as I see fit. So we'll go with that. So it's 56,000 and 14 thousandths. So that's 3, so that's plus, oh no, it's going to have a decimal point even. 0.014. That's 14 out of the maximum 999, yeah, and then go up. Okay, so I think it's 56,000.014 is what I'm going with. Next one. 19 and 19 hundredths. Okay, so that's 19 and 19 hundredths, so that's 0.19. Okay, that makes me more confident that they do mean decimal points here. Because if it meant 19 and 19 hundredths, for example, then that would make no sense. So, okay, so I think they do mean decimal places. So I'm confident this is okay. 57 and 48 10,000ths. Okay, so 57. Now a 10,000th is going to have 4 decimal places, and we want 48 of them. So 0048. So that's 48 out of the full amount, which would be 10,000, giving me 1. Yes. And then 23,005. 23,005. Not and 5. 23,005 and 4 tenths. And 14 what? Okay, hang on. Okay, so there's a semicolon between each number. I'm going to have to recheck this, aren't I? Okay, 56,000 and 14 thousandths, yes. 19 and 19 hundredths, yes. 57 and 48 10,000ths, yes. 23,005, so that's 23,005. And 4 tenths, so 0.4. Cool. And then oh, and 14 millionths, but there's a semicolon there, so I think that's going to be the next number. Okay, 14 millionths, so that's 0. Now, millionths is 6 decimal places, so 1, 2, 3, 4, and we have 14 of them. Great. Okay, so they are the numbers. Add them and express their solution in words or numerate. So I assume numerate means write it out as a number, so that's what I'm going to do. Right, let's add them. So we've got a 4 in that column, and then we have a 1 in that column. Then we've got an 8 plus a 0, and nothing else. So that's an 8. Just going to check these off. So we've done the 4, the 1, the 0, and the 8. Then we've got a 4 and a 4 and a 0. So that gives me another 8. So it's the 0, the 4, and the 4. Then we've got a 1 and a 9 and a 0 and a 0. So 1 and 9 gives me a 10. So that gives me a 0 and carry a 1. And then cross off those. And then finally, we've got a 0, 1, 0, 4. So that's a 5 plus 1 to 1. So that's a 6. So that's a 6 point. So we have the decimal. And this should be a bit easier, hopefully. 9 plus 7 is 16 plus 5 is 21. So carry the 2. 0 plus 1 and 5, so that's 6, that's 8, 81. The hundreds is a 0, and then that's going to be a 9 and a 7. All right, so 79,000. I think it's 79,081.608,814. Or 79,081.608814, as we would say today. All right, that's question 1. Fun. Question 2. All right. Of course, could have just put that into a calculator, right? Would have been a lot easier, but not allowed. What is the difference between, I can't even read this, 3 3/4 plus, okay, 3 3/4 plus 7 5/8? What is the difference between that and 4 plus 2? I think it says 3/4. All right, I'm going to go with that. Plus, no, not plus, the difference. So the difference means to subtract them, doesn't it? So assuming difference means subtract, minus 4 plus 2 3/4. 4 plus 2 3/4. All right, cool. So let's make that easy. So we're going to cancel out most of that. So I can get rid of 3 3/4, get rid of 2 3/4, and make that a 3. And so then it's just nice and easy. It's just 7 5/8 minus 3. So the answer there is 4 5/8. Cool. All right, like this. 3. In multiplying by more than one figure, where is the first figure in each partial product written? And why is it so written? Is this asking me to describe log multiplication? I'm going to just describe log multiplication, I guess. In multiplying by more than one figure. All right, so let's do an example. So if I have example, let's do like 12 times 21. Right, I could do this easily, but let's do it using log multiplication. So if I were to work this out, multiplying by more than one figure, where is the first figure in each partial product written? So I think this is telling me to split it up into the tens and the units and then do like a table, is what I'm guessing. So I'm going to say that can be written as 10 and 2, and then we've got 20 and 1. We're going to do like this. Been a very long time since I've done this sort of table situation, I think. So then you do 20 times 10, which gives you a 200. 20 times 2 is a 40. 10 times 1 is 10, and 2 times 1 is 2. Okay, so I think they are the partial products. Again, my attempt at understanding what this means. Where is the first figure in each partial product written? Okay, so what have I worked out? I've done 20 times 12 equals 240. So 20 times 12 is 240. And then I've done the 1 times 12 is 12. So the first figure. So I'm going to assume the first figure of the first partial product is right at the beginning, he says. But that wouldn't necessarily work, would it? No. Huh. I think it's just, there's clearly a method here that I don't know. But all I want to do is kind of just add these things together, right? Is do that added together. So the answer is 252, which does sound like 21 times 12. If I'd calculated the normal way, I would have done 10 times 12, doubled it, and added 12, which is 252. So I'm not really sure what they want from me, to be honest. Don't understand the method. So I've attempted to do long multiplication. I assume at some point in there is what they're asking for. I don't know, 1866. What can I say? Even I'm not that old. All right. Anyone else any other ideas? Of course, please let me know in the comments. That is, I think that's the only method I can think of. All right, let's move on to 4. Keep it moving. If the divisor is 19, okay, the quotient 37 and the remainder 11, what is the dividend? Okay, I like it. So it's like x over 19, divisor is 19. I don't know the dividends, that's x. So x over 19 is equal to 37, so it goes into it 37 times, and the remainder 11. 37 lots of 19 plus 11. Yes. So the quotient is 37. So 19 goes into it 37 times, remainder 11. Yeah. So therefore, so it's not x over 19. My bad. It's x is equal to that. Yeah. X is equal to 37 times 19 plus 11. Right. So let's work that out. So that is, it would be 640 for 20 minus a 19. So that's 621 plus 11, which is 632. So I think the dividend there is 632. Question 5. Rapid, love it. Oh, what is the quotient of... Here we go. What is the quotient of 65 BU? Don't know what a BU is, but we will Google what a BU means because I don't know. 65 BU, bushel, maybe. 1 PK, 1 packet, maybe, don't know. 1 PK. 3 quarts, I think, 3 QT, divided by 12. Right, so divided by 12, and they want to know what is the quotient of 65 that. What is the quotient? So what's like the biggest thing that goes into it, maybe? Interesting. So I'm going to assume, I'm not sure what that means, because I'm assuming here there's going to be a conversion, some number of QTs, let's call them quarts, I don't know what the answer is. Some number of QTs is going to give you a single PK. Some number of PKs will give you a BU. Again, no idea what these mean. So there's going to be a way of converting units. So I could turn this whole number into QTs and then divide by 12. That's what I'm going to do. Okay, I'm going to look up because I have no clue here. So again, if you know this, very impressive. Historical knowledge of units, I haven't got a clue. So I'm going to Google this to work out what the relationship is between QT, PK, and BU. Then we'll convert everything to QTs and then divide that number by 12 and get the full quotient, and there'll be a remainder. All right, so 8 quarts is 1 peck. Interesting. So not a packet, made that up. Right, so 8 QT equals 1 PK. Okay, awesome. And then how many pecks are in a BU? It is a bushel somehow. So 1 peck is a quarter of a bushel, so 1 bushel is 4 pecks. So 1 BU equals 4 PK. So 65 BU is 4 times 6500, 260 PK. So we have, right, and then what's that in quarts? So multiply by 8. Okay, equals 260 times 8 quarts QTs. Okay, so 260 times 8. So times 2 is 520, so it's 2,600, 2,080, I think. So that's 2,080 QT is 65 bushels. These words are ridiculous. 65 bushels is 2080 quarts. But then we've got another 3, and we've got a single PK, which is another 8, so plus another 11. So total, okay, so the total is 2091 QT, And now we divide that by 12, right? Yes. So divided by 12, 2091, divided by 12 is, long division. I'm just going to guess. How many 12s go into that? So it's at least 100. It's not quite 200 because I'm, how many am I below? I'm 309 less than 200 of them. So how many 12s go into 309? 309 is how many 12s? That's 12 times, oh god, 25, yes, plus 9. So I think it's 175. Is that what I'm saying? Okay, let's just check. I think it's 175, but let's check. So 12 times 175 is 1750 plus 2 lots of it, which is 350. So that's going to give me 2100. No, that's too many. Right, so not quite that many. So it's 12 times 174. Yeah, so 12 times 174 is therefore going to give me 1 less 12, so that's 2088. So there'll be 3 left. Is that what I had to do, right? No, it was, hang on. It wasn't the remainder, it was the, what is the quotient? So therefore the quotient is 174. And I'll just put here remainder 3. Cool. All right, learn something new. 6. Which one of the fundamental operations or ground rules of arithmetic is employed in reduction descending? What on earth is reduction descending? 1866 exam. Reduction descending. Right, I'm going to have to Google what is reduction descending. I think this might be another question I am unable to answer. But nonetheless, let's see what Google says. So the internet reliably informs me, according to the Free Dictionary, the operation of changing numbers of higher into others of lower denomination is reduction descending, i.e. dollars to cents. Okay, so I think it's kind of what I just did, I think. Again, according to the Free Dictionary, reduction descending means taking the larger denomination and putting it into smaller denominations. So I've just gone from bushels and turned it into pecks and then into quarts. So that was a reduction descending. Okay, so I'm just going to put here, e.g. dollars to cents is the other example they gave. Okay, makes sense. Makes sense. So what was the actual question asking me to do now? Which one of the fundamental operations of arithmetic is employed? So to go from, so let's suppose I had like $5, then that's equal to 500 cents. So to go from the higher one to the lower one, you are multiplying. So I would argue that multiplication is the fundamental operation that we're wanting to use. So, so multiplication. So you multiply the higher denomination to get the lower one. To get the lower one. And I have just exemplified that in question 5, pretty much. Give an example. Okay, example, e.g., I just did it. $5.12 is 512 cents. Is 5.12 times 100, which equals 512 cents. Okay, so I assume, again, I don't know what fundamental operation is in the context of this test and in the context of 1866. I'm assuming it means one of the things I have tattooed here, plus, minus, multiply, divide. Assuming it's one of those 4. Which if it is, we're doing multiplications. Cool, right, 1/4 of the way through. Question 7. In exchanging gold dust for cotton, by what weight would each be weighed? exchanging gold dust, that common method of currency and payment, for cotton, by what weight would each be weighed? I have no fucking clue, is my answer to that question. No idea. Literally no clue. I don't even know if Google will tell me the answer here. I mean, I'll have a look, but what would you weigh gold dust for cotton? All right, so I am speechless. So gold dust is going to say be weighed in something. What do you weigh gold dust? Gold dust. Not even gold dust. Right, what on earth would you weigh gold dust? Units of measure for precious metals. 24 troy grains to a pennyweight. I mean, there you go. Or troy ounces, in fact. Okay. So it reckons... Okay. I'm going to note this down because I haven't got a clue. 24 troy grains equals 1 pennyweight. It is written DWT. And then 20 pennyweights is a troy ounce. So 20 DWT is 1 troy ounce, which is written TOZ. All right, well, that's how you weigh gold in troy ounces, I guessed. And then what would you... Cotton? Cotton. What do you weigh cotton in? Cotton weighed in... what is cotton weighed in? Let's have a look. Oh, the imperial unit for measuring fabric weight is ounce per yard squared. Yeah. All right. Or GSM, but GSM is grams per square meter. All right. I'm going to assume then it's ounce per yard squared. Yeah. All right. Weighed in ounce per yard squared. All right. So ounce per yard squared versus troy ounce. Sounds believable. Again, I am literally just typing. I am writing out what the internet is telling me when I ask this question. So I have no clue. All right, number 8 is much better. We're getting back to actual maths here rather than random facts from history. What is the only even prime number? We know that one. 2 is the only even prime number. Even. So the definition here, in case some of you were wondering, a prime number is a number that only has itself and the number 1 as factors. They're its only divisors. So, for example, 3, 1 and 3, but 4 is 4 and 1 and it's 2 times 2. So 2, just by, I guess, happenstance of being very small, 2 only has 1 and 2 as factors. So therefore, by the definition of a prime, 2 is a prime, the only even one, because any even number after 2 will always have 2 as a factor, because that's how we define even numbers. All right, so we can move on swiftly from that one after the gold dust and cotton one, honestly. 9. Ooh, how many weeks is 8,568,456 minutes? Right, this is fun. Like this. So I'm going to have to divide that by 60 to get hours, and then from hours get days, and then get weeks. So we're going to kind of work up for like that way. So we want to divide by 60. Oh God, how am I going to do that? So I'm going to have to remember, literally try and remember long division from quite possibly 20 years ago. 60 into 8,568,456. So I can't remember how you do this. So it doesn't go into 8, it doesn't go into 85, it goes into 85 once. So I think I put a 1 and then carry the 25. And then in 256, how many times in 256? Let's see. 60 in 256 is, 4. And then remainder of 16. 256, the remainder of 16. So now into 168 is 2. don't know if this is right. But anyway, and then we've got a remainder 48 into 48 doesn't go into 484. 60 into 484 is 8. Yes. 8 remainder 4. Yes. So now it's literally just 456. How many 60s go into 456? That's going to be 7 remains of 36 and 36 minutes. Okay, so I don't trust my long division at all, and I'm pretty sure I didn't use the right method there. So I'm just going to check and do 60 times this number to see that I get the 8 million, just to be safe. Check. 60 times 1 times 14,000. No, that's not big enough. Because it's not 7 of them, it's 70. Oh, hang on. I think there was a 0 somewhere that I've missed. I've missed a 0 somewhere. Okay. No, have you? Wait. Yes, it's 142,000. Okay. Missed a 0, but let's just do 60 times 142,870. Right. So that's 142,870, 0, and then times 6. So that's, oh gosh, again with the multiplications, man. 6 million from the first number, and then we've got 428,000. What's 428,700 times 6? So times 10 and then times 5. All right, so it's equal to 428,700 plus half of it. So 214,350. Yes, right? Okay, I think it's right. So that's then 1,200. So that's like a 2, carry the 1. 8 and 3 is 11. That's a 2, carry the 1. 2 and 4 is 6, 7, 5, 2. 2572, 200. Okay. Wait. That's, what have I done here? I've done that times, what have I done? Oh, it's 6 million plus that, so that's 8 million. Ah, yes, okay. So I get 8,572,200. Okay, so it's too many. Right, so it's not quite that. I've gone, how many am I away now? Minus 8,500,000. This is the worst possible arithmetic ever, but I think I'm going to get there. 456. Okay. So there's like another 3,000 there. Not quite 4,000. It's 256. 4,000 minus 256. So that's 3,744. Too many. So then what's that in 60s, which is 60 times 60 would give you 3,600. So that's 60, 62, 63 too many. Subtract that from the 142,870. So I think then what we've got here is 142,807 hours. Plus 36 minutes. Okay, so it's obviously a point something. I don't think I meant to do the point. I'm not going to work out the point. Right, I obviously could. 36 minutes is 0.6 of an hour, for example, but I don't really want to give decimal points of a week. Not helpful. So I'll leave the remainders in terms of hours, days, and minutes. I think that's fine. Okay, so we have a value for hours. So now I'm going to divide that by 24. So how many days? So how many days? Okay, so I need to do 24 into 142,807. Cool. And try and not mess it up this time. So it's 24,000 times 6 is too many. Well, let's just do 6 times 6. So 24 times 6,000. Let me just redo that. So 24 times 6,000 will give me, times 6,000 is, so 24 times 6 is 144. So it's 144,000. Okay, so it's not quite 6,000 of them. So then we subtract off 142,807. What are we left with? So that's going to be a 143. So it's 1,193. 1,193. How many 24s go into 1193? 24 times 10, 40. Okay, 24 times 40 is 960. So that then leaves another 233 left. So that's not quite 10, that's another 9. Okay, so 49 of them. Yes, so 49 times 24. So not quite 50. 50 would be 1,200, yes, okay. So is 1176 plus, with the remainder then of not 24, of 17. Okay. Okay, so I think, but that's too many, isn't it? Yes, so I need to go 20, no, we need to subtract off that. No, I need to subtract off the 50. Yeah, so I think it's 5,950 weeks. Days. Okay, 5,950 days. Right. And I think there's there's some number of hours, who cares? It's whatever. Not bothered anymore. So then how many weeks? So you have to divide by 7. So divide by 7 to get weeks, which is finally what we're trying to get. Okay, so 7 times 800 is 5,600. And then we need the 350. So 7 times 50 equals 350. So it's 850 weeks. Therefore, 850 weeks. Okay, we're going for whole weeks. It's 850. That's my answer. All right, number 10. That was a long one. Number 9. Lots and lots of very bad long division and multiplication done by me. But anyway, we have an answer. 10. To what term in division does the value of a common fraction correspond? To what term in division does the value of a common fraction correspond? I have no idea. 1866 arithmetic exam. Term in division of I have a common fraction. So common fraction to me is when you have two numbers and you put them over the same denominator. So, okay, so let's think about that. So common fraction is like, e.g., I don't know, 3/4 plus 1/6 is common denominator. They both go into 12. So that's 9/12 plus 2 out of 12. So it's 11 out of 12. So there, the common fraction, therefore, is the 12th, the 12 on the bottom. That's how I would think about it. So what term in division does the value of a common fraction correspond? So if you're dividing, then okay, so here you would say 12 is the lowest common multiple of 4 and 6. So I think my interpretation here, again, no idea if this is right. I think what it's asking is, how do you get the denominator for your common fraction? It's going to be the lowest common multiple of the two numbers, or the two fractions you're trying to add together. That is my attempt at that question. Again, probably had different meanings, and I'm not really sure. Division, I think, is related to fractions. Kind of feel like it's fuzzy. I really have no clue. But that to me makes sense and is pretty mathematical, so I'm going to go with that. 11. What is the product of a fraction multiplied by its denominator? Now this one I know. Okay, so a over b times the denominator, which is b, will always equal a, i.e. Fraction times denominator always equals numerator. Boom, like it. That is my kind of question. 12. What is the rule for the multiplication of decimals? What is the rule? Okay, let me think. So if I have like 0.12 times 0.04. So what is the rule for the multiplication of decimals? Okay, so how would I do this? So what I would do is say that's 1.2 times 10 to the minus 1. I put it in standard form, which I'm pretty sure is not what was done in 1866, times 4 times 10 to the minus 2. Oops, that bracket goes there. So in standard form, it's that. So in standard form, that would now give me 4.8. No, it wouldn't, because I need to put them in the same standard form, don't I? So scrap that. So you would say it's 0.12 times 10 to the minus 2 times 4 times 10 to the minus 2. Probably didn't have to do that anyway. Because now you just multiply everything through. So it's just 0.12 times 4, so it's 0.48 times 10 to the minus 4. Which in standard form would be 4.8, yeah. So I didn't need to do it that way, but anyway. Minus 3. Okay, so that's an exemplification of how I, right now, in 2025, not 1866, would multiply decimals. So when it says, what is the rule for the multiplication of decimals? I'm going to assume the number of places, it's to do with the number of places, isn't it? Yeah. So, so what would this actually be? So this one would actually be then, let me think about this. So it'd be 0.1, 0.48, 0.0048. Okay, so I think the rule is the number of decimal places in answer is the sum of the decimal places of terms in product. So I think that'll hold. So the idea here being, I've done an example where I have a 2 decimal places number multiplied by a 2 decimal place number, and my answer I give in 4 decimal places to sort of carry through all of that information. So I think that in general will work, is my understanding of standard form and decimal places. So I think the rule is going to be something like that. Again, probably haven't stated it entirely as 1866 exam would like, but I think that's what it's getting at. Question 13. How is a common fraction reduced to a decimal? Give an example. I will very happily give an example because I have got no other way of explaining it. Okay, so how is a common fraction reduced to a decimal? Okay, so I'm going to assume here it means you have 2 numbers, you would add them by putting them over a common denominator, which again, I'm interpreting to mean common fraction. You get an answer. So the answer I had above, okay, so e.g. Above, what did I look at? 3/4 plus 1/6. Okay, so I had 3/4 plus 1/6, which we said convert through the lowest common multiple into 9 out of 12 plus 2 out of 12. So we get the answer 11 out of 12. Now to convert to a decimal, twelfths. I'm not actually sure what twelfths are, so this is going to be fun. Should have picked an easier number. Tell you what, I'm going to change my numbers. I'm going to change it. It doesn't say I have to pick a hard number. So I'm going to change this to be 3 over 5 plus a half. Redoing that with easier numbers, 3 over 5 plus 1 over 2 is the same as 6 over 10 plus 5 over 10, which is 11 over 10. Okay, so I would now calculate e.g. the value of 1/10, one lot of the denominator, and then multiply the numerator. So to exemplify, so here, this is 1 over 10, which equals 0.1 as a decimal, and then multiply by 11 to get 1.1, which equals 11 over 10. So there is an exemplification. I obviously could have done twelfths, I just don't really want to work out. I think it's 0.083333333. Now I've just actually thought about it. But anyway, that would be 1/12, and you multiply that by 11 to get the other one. It looks nicer here with these non-recurring decimals. All right, 14. What is ratio and how may it be expressed? Illustrate by an example. All right, so example, e.g. A ratio of 2 to 3 means what does it mean? It means 2/5 of the total is in, let's say, the left-hand category, and 3/5 in the right-hand category. So here I've supposed that 2 is in the left bit, 3 is in the right bit. The ratio between the left and the right is 2 to 3. So it means that 2/5 is in the left and 3/5 is in the right. So more generally, you would say a ratio A to B means A out of A plus B on left and B out of A plus B on right as proportions of total is how you would do that. Okay, cool. I think I gave an example. 15. If 20 units, 27 tons, 27 old school tons, spelt T-O-N-S, 3 QRs, don't know what that is, 3 QR, and 15 pounds, I know what a pound is, 15 lb, of coal, okay, and that costs $217.83. That seems cheap. In I assume in today's currency, at least that feels like it would be cheap, though I'm sure there's a lot of inflation that's happened in the last 159 years. And yeah, 159 years now, wow. All right, $217.83, okay. $217.83. Fabulous. And we want to know what will 119 tons. Okay, then what is the cost of 119 tons, 1 QR and 10 pounds? Okay. So I could do as before and look up the conversion. Again, obviously I have no idea. The conversion of pounds to QRs, which I assume is a quarter, pounds to quarters, quarters to tons, rewrite the whole thing in pounds, and then work out how much 1 pound of coal costs based on the figure given. Convert the second one, the amount I need to work out, convert that into pounds, and then do a multiplication. But it feels like that's going to be a nightmare because of all of the numbers and decimal places. So I'm going to try, at least first, and sort of cheat a little bit and just do a simple multiplication and see what happens. Might work, might not. We'll see. So I'm going to multiply by 4 to start with. So if I take the above and multiply by 4, so if I do times 4 of everything, then we've got 108 tons, 12 QR, whatever that means, and that's 60 pounds, and that's going to cost 4 lots of 217.83. All right, so I'm going to have to work that out. So that's 868, and then it's plus 83 cents times 4 is 332, I think. Right, 83, yes, plus that. Okay, so it's 871.32. Right, so now we need an additional something. So I'm going to have to look up pounds to quarters. All right, come on, internet. Right, okay. There are 28 pounds, I think. Yes, the quarter is 28 pounds. Okay, so let's just note this. 1 QR is 28 LB. Sweet. So what we've really got here, plus 2 QR and 4 LB. Sweet. Is what that 60 pounds is equal to. And then a quarter is 1/4 of a hundredweight. I don't know how many hundredweights are in a pound. How many QR in a ton? Not hundredweights in a pound, hundredweights in a ton. In a ton. The imperial ton is 2,240 pounds. Okay. So 1 ton equals, I just had it there, 2,240 LB. So if there's 28 pounds in a quarter is what? Oh, it's 20 hundredweight. Okay, wait, hang on. So 1 ton is 20 CWT, and how many? And a quarter is equals 80 QR. So 80 times 28 is that. Yes. Good, that's correct, yes. Okay, so 1 ton is 80 QR. Amazing, yes, which is 2,200, that's correct. So, so we're good. So we've got 108 tons, right, so that is equivalent to 108 tons, 14 quarters and 4 LB. Right, and how many more do I want then? I want another 11 tons, but I don't know how much 11 tons costs. Oh, this is so annoying. Oh, I really don't want to work it out. God damn it. So annoying. I'm going to have to work it out. Ugh. Okay, you know what? I think we've all had enough of me doing a very bad job of long division and long multiplication. So I've reached that point. I'm going to use a calculator. I'm sorry. Stamina's running out. I'm going to use a calculator and just get the answer. So this is how you would work it out, because I'm intrigued to see what the answer is. This is how you would work it out. So what do we know? We know that 27 tons, 3 quarters. Okay, so 27 times 2240 is the pounds, plus the quarters, 3 quarters. Each quarter is 28 pounds. So plus 3 times 28, and then plus the last amount is 15 pounds, which equals some number of pounds, and that costs 217.83. So, using a calculator, let's work this out. So 27 times 2240, 60,480 plus 3 lots of 28, I can do that one, is 84, plus that one and plus 99. So that's 60,579 pounds. So what's the cost per pound? So what we're going to do is do that number, 6579 divided by, and we'll do it in cents. So 21783. So it's 2.78. So that's divided by 21783 cents equals 2.781 pounds per cent. Okay, so for a cent you get 2.7 pounds of coal. So how many do we want? We want, what amount? Let's see, 108 tons. Wow, that's a big number. No, 119 tons. We want 119 times 2240 plus 12 quarters. No, not 12 quarters. 1 quarter, which is plus 28. And how many pounds? Plus 10 pounds, plus another 10. So we want, using calculator again, 119 times that, plus 38. 266,598. 266,598 pounds. So we want 266,598 pounds, and we know how much pound we get per cent. So I need 1 over that then, don't I? So, and we have, we pay, what's that? 21783 divided by 60,000. That's cents per pound. So I actually want 1 over that earlier number. So therefore, the cost is 21783 over 60,579. Cost per pound multiplied by the number of pounds I want, 266,598. Right. See what that is? $958.63. Which seems sensible based on my earlier estimate of 4 times the price. 16. Find the cost of the several articles and the amount of the following bill. All right, well, this sounds fun. So Utica, October the 1st, 1866. AP Jewett to Samuel Palmer, Doctor, to oh God, here we go. 16,750 feet. 16,750 feet. Okay. Of board at $12.5 per M. What's an M? At $12.50 per M. I don't know what an M is. That's mile, maybe mile. Let's have a look, shall we? What does M mean? Okay, I think it's mile. All right, so we're going to go with mile. M for mile. All right, and so 1 mile is 5,280 feet. 5,280 feet equals 1 mile. Okay, cool. Yeah, I can work that out. Fine. And then we got a couple of others. And then we got 1,750 feet at a different cost, $24 per mile. That's more expensive per mile. And then finally, 3,500 feet at $25. Okay. Per mile. Right. Okay, so again, it's very similar to before. We're doing a conversion. We're going to work out the cost per foot or the cost per 10 feet, for example, and then just multiply that by the number that was actually purchased. So first one, for example, then it's $12.50 for 5 to 80 feet. So it's therefore $12.50 divided by 528 for 10 feet, which means we have that number, which again, calculator, 12.5 divided by 528 times 1675 for item 1. Okay, so plug that in. So that's equals 39.65 for item 1. And then now item 2, similar calculation. We know that it's 2400 divided by 528 per 10 feet. And so we want that 24 divided by 528 multiplied by how many lots of 10 feet did we buy? We bought 175 lots. Okay, so that's now going to be $7.95. Does that sound about right? It does, because it's a much shorter amount. Yep, cool, that's fine. It's like, yeah, that works. And then finally, for item 3, we want $25 over 528 per 10 feet. So that gives me 25 divided by 528 times, how many lots of that did we get? 350. Which is coming out at $16.57. So the total of the bill is $39.65 plus $7.95 plus $16.57. This one I will do in my head, which is going to give me, regrets it already, as at the first two, so that's $39.60 plus $8, $47.60 plus the second one is $16.57, so that's going to be 47.53, 64.17, $64.17, and that I think is the answer to question, what was that one? 16. Woo! All right, so that is Mr. Samuel Palmer, I think, is paying, yeah, how much Samuel Palmer is paying to AP Jewett for that board, very expensive board. Okay, question 17. What is the length of the side of a cubical box which contains 389, oh God, so 389,017 solid inches. I'm going to assume a solid inch. Surely a solid inch is an inch cubed. I'll double check that, but I'm going to assume that means an inch cubed. I'll check. So it's a solid inch. Yes, it is indeed 1 cubic inch. Okay, so 1 inch cubed. Great. So we want x cubed for the side length because it's a cube. So we have x, all the dimensions are x. So x cubed equals 389,017. So we want x to be the cube root of 389,017. So again, calculator, aren't we? Cube root of 389,017. I do not know that one. It's 73. Very nice. All right, so it's 73 inches. Sweet. Nice. Okay, question 18. What is the present worth of the following note discounted at bank, and when will it become due? No idea. Right, so $100, and this was dated October 1866. So add 90 days will give me the due date, won't it? Yes. 90 days from the date, for value received, I promise to pay to the order of John Smith $100 at the Albany City National Bank, John Brown. So what is the present worth? So I'm not entirely sure what is going on with this question. I was expecting there to be an interest rate or some kind of I don't know, way of calculating the current value of the $100. Maybe there's like a standard way, like per day, maybe that it like increases. Maybe it's 100 divided by 90 days, perhaps. Literally no clue. Or maybe there's like a standard way that the banks worked in 1866, right? That could also be a thing. Today you would be given your interest rate, your APR, your annual percentage rate, or something of that nature. So I literally have no clue what it's now worth, but I can at least calculate the due date in 90 days. So let's just do that. Right, so plus 90 days from October the 11th. So 30 days has September, April, June, and November. Right, so if I add on 21 days, then that'll take me to the 1st of November. And then plus another 30 will take me to December the 1st, because November has 30 days. December has 31, so I need to add 31. So plus 82 will take me to January the 1st, and then another 8. So plus 90 is going to be, I think, January 9, 1867 is when that will be due. How much it's worth? No clue. But we're going to move on now to the final 6 questions, the last quarter of the exam. Let's see if it saved the really tricky ones for the end. I mean, some of these already been hard, like, right, gold dust, honestly. Okay. Involve 5, really hard to read, small text. Involve 5/8 to the 7th power. Okay, so we got to do 5/8, and assuming here involve means raise to the power of 7. So how many of these could I work out? Well, I can do a bit of it, and then I'll probably give up and use a calculator. But it's 5 to the 7 over 8 to the 7. So what's that? 5 squared is 25, so it's 5 times 25 times 25 times 25 divided by 8 to the power 7, so that's 8 times 64 times 64 times 64. Right, so again, I could work those out, I just don't really want to. I've just broken the powers up into the squares. Makes it a bit easier, but again, I'm just going to put this in the calculator. I just want to get to the end of this exam. So 5 to the 7 is 78125 on the top, 78,125 on the top, and then we're dividing by 8 to the power 7, which is coming out at 2 million, wow, much bigger number, naturally, 2097152. So it's a very small number, as you would expect. You have a number less than 1 and keep raising it to higher and higher powers. It gets smaller and smaller every time you raise it or multiply it by itself. Cool. All right, 20. Nearly there. Nearly there. What is... I said the hard ones were coming. What is the square root of 0.004304 6721? Okay, this is amazing. What a question. Right, how on earth would I work that out? So I want to know the square root of this, right? So let's call that x. So, of course, I would calculator it, and probably will. But I do have an interesting idea about how I might begin this question, which is to say, what you're looking for here is what is the square of this number, right? So let's suppose this is y squared. So if we were to think of y squared is 43046721, so that's 43,046,721. Then y of that, then we can compute y, right, which is going to be equal to something, the square root of that number. And then that's going to be the answer, I think. Then x is, then what would it be? Then x would just be 0.00, no, 0.0 times that, I think. 0.0 and then just y dot 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 dot. He says, I think that's what it would be. Well, let's check my theory. So let's square root y as I've written it. Again, I could probably try and guess it if I really had to, but It's already been a drag. So let's just square root this number. So square root of 4,430,46,721. Right, square that, 6561. 6561. So I think, i.e. x is equal to 0.06561. Now I'm going to check that. So let's just do the square root of the actual number they've given me and see if my theory holds. 0.0043046,721. And it does. Okay, brilliant. So that is x. So I think that's how you would actually work it out, deal with the full number rather than the decimal. And I just wanted to check that worked because I just wanted to check with the extra 0. So the idea here, we talked about this in an earlier question, multiplying decimals, is this, not that 0, the 0 here in front of the y. So this will become the first, this will become 0.00, etc., which is what's going to give us the number we want to square root. So putting that one decimal place there, when it's squared, is going to give you a second one, a second 0. So that's why I thought that would be the answer. But again, I would need to work out 6,561 squared and see that it was that number, 4 million, whatever. But anyway, there's the answer. 21. All right, conversions again. Sold 9 1/6 hundredweights of sugar. Okay. 9 1/6 CWT of sugar at $8.25 per hundredweight. So at $8.25 per CWT. Great. And lost 12%. What? And thereby lost 12%. So how much was the whole cost? Okay, so I can work out how much was received, and that would be 0.88 of the total. And then I can divide by that and get the original cost, I think, is what this is asking me. Anyway, let's spell it out, and maybe it'll make more sense. It makes sense in my head. Okay, so we want to do 9 1/6 times $8.25. All right, so that's $72. Plus $72 plus 9 times that, which is $2.25, and then plus 1/6 of 8.25. Okay, so 1/6 of 8.25. What's 1/3 of it? That's going to be 275, I think, right? Yeah, 275. Yes. So half of that. So it's 2.75 divided by 2, which is 1.375. Okay, so I think the sale was equal to 74. Let's work this out now. 74.25 plus an additional 138, assuming we're rounding up there. So I think the sale, therefore, was 75 and 63. Okay, but that is which is at 12% loss. So i.e. If the total cost is x, let's say, so x is equal to 0.88 times the amount that we sold it for, and it's 0.88 because we've lost 12%. So x is 0.88. No, wait. No, 0.88x. Sorry. 0.88x is equal to the amount we've sold. Yes. That's it. I knew what I meant in my head. 0.88x is that. So x is equal to 75.63 divided by 0.88, which will, of course, make the number larger. So 75.63 divided by that. 75.63 divided by 0.88 is 85.94. So $85.94. So I think that was the original total cost. And we've lost 12% of that. and sold it for 75.63. Cool. Yeah, going with that. 22. A person owned 5/8 of a mine. Okay, so 5/8, and sold 3/4 of his interest. Okay, sold 3/4 of the 5/8. Yeah, cool. For 1,710. Okay, now this question I like. 1,710. It's going to ask me what was the value of the whole mine. Right, cool. Whew. So 3/4 of 5/8. So 5/8, we're going to use the common denominator thing, is going to be in 32s. So 5/8 is 20 out of 32. So 3/4 of 5/8. Oh, I could have just multiplied them, I guess. Is 15 out of 32. Okay, so 15 out of 32 was sold. So therefore, 15 out of 32 of the mine of X equals 1710. So X is simply 1,710 times 32 divided by 15. Right, at this point, I might as well put it in a calculator. We've given up trying to do it by hand. This one you definitely could do by hand though. So 1710 times 32 is that number divided by the 15. So 3,648. So the cost of the whole mine is $3,648. Feels cheap, but again, with inflation, might be a rip-off. I don't know. 159 years is a lot of inflation has happened in 159 years. All right, this is great. 23, penultimate question. Nearly there. I'm excited to finish this. When it is 2 hours 36 a.m., okay, so 02:36 at the Cape of Good Hope, at Cape of Good Hope. Where on earth is the Cape of Good Hope? Is my question. What is the time at Cape Horn? Is it 18 degrees east? The Cape of Good Hope. Is that... Oh, I think that's South Africa. I think that's South Africa. That would make sense being 18 degrees east. Yes. I think that's South Africa. Okay. What is the time at Cape Horn? Interesting. So Cape Horn is the tip of South America, which I think is Chile. So I've been to both of these countries, so I should know this. Relative to the UK, South Africa is +2 from GMT, which is UK time. And Chile, I think, is -3. Yes, because you're really east. On South America, it becomes quite east. So I think it's just -3 from GMT. So I think there's a 5-hour difference. So 5 hours earlier at Cape Horn. Is that right? Yes. Assuming I have got the countries right, which at this point is kind of a guess. But I'm pretty sure they're the Capes. It's the South Africa tip, and South Africa tip is Good Hope, and I'm pretty sure Horn is... The longitude seems to work, I think. Again, based on the UK being at 0. Seems to work, so... Okay, so 5 hours earlier at Cape Horn is... Does it give me a date? No. Okay, so it's 5 hours earlier. So that's going to be 9 o'clock at night is 21:36 the day before. I think there's 5 hours between them, so just 5 hours earlier than 2:30 in the morning is 9:30 the night before. Awesome, he says. Again, no idea if any of these are right? There's obviously not a mark scheme. Why would there be a mark scheme for an exam of 1866? All right, last one. What is the cost? Oh, conversion, of course it is. 17 tons 1 quarter, at least I know what these mean now. I've definitely learnt a lot about old imperial units. 1 quarter and 17 pounds. 17 pounds of potash. Oh, amazing. Potash, which is 50, I don't know what potash is. 53.80 per ton. Amazing. $50.80 per ton. Okay, so do I remember this? Well, I'm going to scroll up and find it, aren't I? So for tons, we did a conversion way up here. So a ton is 2240 pounds. Yes, 2240 pounds. So that's 53.80 for 2240 pounds. So how much is £1? So that's 53.80 over 2240 dollars per pound. Awesome. Now, how many pounds do we have? We want 17 times, was it 2240? I'm pretty sure it's 2240. Yes, I'm going to back myself. Might regret that. 2240 pounds plus 1 quarter, which is 28 pounds, plus 17. We want that many pounds. Can't be bothered, so let's just check. 17 times 2240. 17 times 2240 is 38,080. 38,080 plus 45. So we want 125 pounds. So the cost for all of that potash, whatever potash is 53.8 divided by 2240 times 38,125. Right, because we want 17 tons. Awesome. That many dollars. So let's whack that in. So it's going to be that amount, yes, times 53.8 divided by 2240 equals $915.68. $915.68. So that's what it's going to cost me to buy all that potash. And that, thankfully, is the end of the exam. Right, 159-year-old exam completed. And I don't really know what to say. That was something, wasn't it? That was quite something. I had no idea what to expect before I started. As usual with these things, completely blind, haven't looked at it at all. Just, here's a cool paper that someone sent me. Thank you, Ryan, by the way, for sending it over. Been sent this paper, like, let's have a go. And yeah, it was something. It was something. Lots of conversions, right? Sort of lots of, here is a set of units. Here is a cost per some amount of unit. How much is this other amount of it going to cost? A lot of conversions, which I guess was a lot of what you were doing, right? If you're running a business or trading or buying anything back in 1866, that's the kind of thing you would need to know how to work out. Having done the exam now, I feel like they must have had some kind of calculator. Obviously not, the one on Google that I was using, but they must have had some kind of calculator for doing these numbers, unless they were just really, really good with long division and long multiplication. So I, as you saw, I started off trying to do it all in my head, and to be honest, it was just taking a very, very long time. So by the end, I was just sort of writing things as fractions and then plugging them into the calculator. But hopefully it gave you the idea of what these calculations would be. Again, I don't know exactly what tools were available in 1866. If there are any historians or anyone who knows more about this watching, please let me know in the comments. I would love to know actually like how these things would have been done by somebody 159 years ago. Because I'm imagining it wasn't all by hand, but could be wrong, don't know. But definitely interesting, right? I feel like I learned a lot about the units that we used back then. I learned a lot about, I guess, the terms they used for things, right? So there was that question, reduction descending, right? So this idea of converting from larger units to smaller, reduction descending. I didn't know what that means. Now I know what that means. I learned all about bushels and pecks. Pecks, wasn't it? Bushels and pecks. The stuff about divisors and quotients was interesting. Sort of getting people to understand the terminology there, which is, again, still the terminology we're using today. Quite liked that. We had to do some subtraction of fractions back in question 2. That was cool. Gold dust and cotton. Great question. Probably your favorite question there. Number 7. The weight in exchanging gold dust for cotton. By what weight would each be weighed? Is just a hell of a question on a maths test. Love that. Only even prime number. Love that one. The weeks one that took me forever. What else have we got? Oh, we had this thing about common fractions and products of denominators. So again, lots of work with fractions, which was interesting. How can you reduce a common fraction to a decimal? Again, conversions, decimals, fractions. Something now we just take for granted because we just do it on calculators, right? You have a button that changes it from a decimal to a fraction, but clearly you would have to have done this yourself, right? 159 years ago, or at least with a different device for sure. And then lots of, again, like bills, right? Understanding bank notes from banks about payments, understanding a bill you've received for buying board, whatever that means. I'm picturing like someone was building a boardwalk, maybe, you know, lots of planks of wood, perhaps. Dr. Samuel Palmer. Okay, the cubic thing was nice, liked that. Think about the bank, we've done that. Powers of numbers, cubing numbers and square roots of numbers. Again, I can't imagine you did that by hand, but I don't know. Right, selling the mine, that was cool. And then the one at the end about time was quite nice. Again, I don't know if I got that right, I haven't actually checked. As you may have guessed by me talking through this and not marking my work, I should have said this at the beginning, there isn't a mark scheme, or at least I do not have the mark scheme in front of me. I cannot find the mark scheme, I haven't been sent the mark scheme. If anyone has access to the mark scheme from the New York State arithmetic exam from 1866, I'd love it. Please send it over. Just go tomrocksmaths.com, click contact, send me an email. I would love the mark scheme, and then I'll do a short follow-up where I can actually mark what I've done. But I'm sure all of you watching hopefully were working through it along with me and were checking my answers, no doubt. Based on previous comments on exam videos, I know you all like to check my answers. As you should, by the way. You should make sure I'm doing things correct. But I thought that was super fun, so I hope you enjoyed it too. I hope you enjoyed seeing this kind of history of maths exams. All of the ones that I've done so far on the channel listed on screen now in their order. I will not add this one to the list. Wouldn't be fair, I don't think, to add an arithmetic exam from 159 years ago compared to the modern exams that you can see listed on screen. I've certainly enjoyed this blast from the past doing maths from 1866, and I hope you have too. If you have, then please do subscribe. But either way, thank you for watching, and I'll see you all soon for some more maths fun. Take care.